In this video, we're going to talk about the concepts and the measurement methods for discharge or flow rate of a stream. So flow rate is the flux of water per unit time moving past a fixed point. So that is a really complicated way of saying that it's the volume of water moving past a specific point in a certain amount of time. So typical units for this would be something like cubic feet per second, which is really common in the US. Gallons per minute are sometimes used in the US, and then cubic meters per second or liters per second are really common internationally. They're really, really important for a lot of different applications. They allow us to better understand our chemical data as well. So TMDLs are a mechanism that the EPA uses to determine allowable pollutant discharges, and also what pollutants are the most important in different watersheds and what's impairing the watershed. That requires something called a pollutant loading. So a pollutant loading is a mass of a specific pollutant in an amount of time. So usually when we analyze for a pollutant, we analyze for the concentrations. We analyze in something like milligrams per liter. But what that doesn't tell us is the mass that we get every day, for example. So, how many kilograms or how many tons or how many pounds of acid or of metal or whatever it happens to be, do we load into this water body every day? And that ends up being important when we look at implementation of some of these regulations. It allows us to interpret our water quality data. I'll show you an example in another video where the pollutant concentrations at high flow versus low flow were very different. And so it allowed us to look at what the mechanisms for the pollution were. It also allows us to understand stream hydraulics in terms of biology and habitat. So, when is it low flow? When is it high flow? Are the low flow conditions stressful? How stressful are the low flow conditions to different taxa? And it allows us to really start honing in on how does that flow rate, how does the flow regime of the stream affect the biology. So when we look at the most basic methods of measuring flow rate, what we use is this equation called continuity of flow. And the continuity equation says that the flow rate is equal to the velocity times the cross-sectional area that velocity is flowing against. So what we will end up measuring is the water velocity, and then we'll measure the cross-sectional area of that stream, and that will give us the flow rate. So many of our methods are these velocity area methods, is what we call them. So when we take flow measurements, we can either take instantaneous measurements or continuous measurements. So we're going to start by talking about the instantaneous measurements. So an instantaneous measurement is exactly what it sounds like. It's the measurement of the flow rate right now. A continuous measurement is either a gauge or a meter that's measuring the flow rate all the time. And so you can look over time at what the flow rate is and how it changes. So this instantaneous measurements are the measurements that we're going to take alongside a chemical sampling. And so this is going to tell us what the flow rate is when we take a chemical measurement. So we will use different methods to analyze this. We'll use current meters. So current meters are measuring the current, or are measuring the velocity of the water. So we still have to measure a cross-sectional area, but these will measure the velocity. And they work in different ways. We have mechanical ones that spin with the water flow rate. We have acoustic ones that use a Doppler to measure the rate of particles moving past a receiver. We have electromagnetic ones that measure the particles moving through an electromagnetic field. And by doing that, they can measure the average velocity of that water. We can use flumes and weirs. These are, they can either be fixed or portable, and I'll show you pictures in a moment of these, but these will basically look at the height of water moving through a known cross-section. So with these, we're measuring the velocity and the cross-sectional area. With these ones, we're measuring the height of the water going through a known cross-section And they've already figured out that that height of water is proportional to the flow rate. And so then we can calculate what the flow rate is from that height of water. The only method that we use that's a truly measuring the actual flow rate, is truly measuring the volume of water per time, is bucket and stopwatch. And that's exactly what it sounds like. It's what he's doing in the photo, where you use a bucket where you see how much time it takes to fill a bucket with water. And so we'll use this where there's a pipe or a culvert, some discharge where we can put a bucket under it. And we'll average 5 readings usually to get a good measurement. If all else fails, and if all your equipment fails and you have no other choice, we use something called the float method. So the float method is basically determining the surface velocity of a water course by timing how long it takes for a floating object to move a specific distance. This is a low quality method because the surface velocity is different than the average velocity of the water column, but if all else fails, this is better than nothing. So when we go in and try to figure out our method selection, there are a lot of different specific ranges that each of these different methods can operate within, and so we'll talk through that a little bit. So we like to use current meters in wadeable and non-wadeable streams that are greater than 0.3 feet in depth. So what you'll see through a lot of this is that we use decimal feet, not feet and inches. And so as long as the current meter can be covered by the water, we can use it in wadeable and non-wadeable. We can use them in wadeable and non-wadeable streams. Some of the current meters that are mechanical, so like this where it has to spin, if the flow velocity is too low, this may not spin, and in that case you need to move to a different method. Portable flumes are great for small channels up to about 0.8 feet in depth. But because the portable flumes are only about this tall, you can't use them in deeper water or water courses where there's enough water to overtop that. We'll talk more about using these in a little while, but typically these are the best for small water bodies. A bucket and stopwatch is great for flow from pipes and culverts where you can stick a bucket under something. And the float method is what you do when you have no other choice, but you still want to measure flow. And the thing to remember with the float method and current meters is that you have to measure the cross-sectional area so that you have velocity and area. So just to show what you do in some of these deeper water bodies, we can use something called an AA meter. So on the previous slide, this is called a pygmy meter. This is one of the most common current meters, and it's made by, or it was originally made by the U.S. Geological Survey. So the pygmy meter we'll use in class, and you measure velocity based on how many times it spins in a certain amount of time. For larger water bodies, you can use something called an AA meter, and this is approximately, or it's 5 times the size of the pygmy meter. And so you can see here, this guy is using it in a deeper wading stream, but once the water gets up to about your hips, it ends up being pretty hard to stand up easily and safely. And so what often is used is a bridge crane application where the AA meter is lowered down from a bridge and measurements are taken across the bridge. This is what was used by the USGS as a standard measurement method until more recently when they have a higher tech solution that measures it by pulling a sensor across the creek. So if you're measuring flow in water that's moving faster than 2.5 feet per second, it will be very, very hard to stand in it. And so if it's moving that quickly, you need to use a bridge crane and an AA meter because that's going to be bigger water. If you're measuring flow that's moving slower than 2.5 feet per second, and I know it's hard to know is it flowing at 2.5 feet per second or not, but really if you're struggling to stand in the water, you shouldn't be standing in it to measure to measure flow rate. So if you can easily stand in the water, you can use that. You can use that smaller pygmy meter, which is our most common meter. So this is an example of a pygmy meter setup. We'll set this up in class, and I have a diagram of this in a moment that I'll show you. So in addition to that, we have to determine where in the water column to measure. So if the water is greater than about 2.5 feet, if it's greater than about 2.5 feet, it again can become hard to stand in it because it gets deeper and there's just more water pressure pushing against your leg. But if you're measuring flow rate in water that's deeper than 2.5 feet, you should be measuring 2 velocities per station. And we'll talk about these stations in a minute. But if in deeper water, you should be measuring velocity at 20% down from the surface and 80% down from the surface. So you should have 2 measurements along that water column that you can average to get an average velocity for that location. In water that's between 0.3 and 2.5 feet, you can measure velocity just at one location, 60% down from the surface, typically using a pygmy meter. If the depth is less than 0.3 feet, you need to use a different method. So usually that will be either a flume or bucket and stopwatch. Alright, so this is the diagram of a current meter setup. So in class we'll use a pygmy meter, but this would be the same type of setup for an electromagnetic meter or an acoustic meter or an AA meter. So the first thing, we have to determine where in the stream we're going to measure. So we want to measure in a run. So streams tend to be divided into pools, which are deeper with slow, very, very slow moving water, riffles, where the water tumbles over rocks, and runs, where water is running more in a not turbulent, so we call that, instead of turbulent, we call it laminar, where it's running much more smoothly, much straighter. And that's where we want to measure the flow. We also want to avoid any large rocks or fallen logs or any other debris in the stream. So we want a pretty straight run section without major obstructions. We then string a measuring tape that's in tenths of feet across the stream, perpendicular to the flow. That doesn't always mean that it's going to be perpendicular to the banks. So it's important to look at the water and look at the particles that are moving in the water and the seeds and things that are floating in the water to make sure that you run this line perpendicular to that flow. So we string this line, this measuring tape, pretty taut across the stream, and then we start measuring velocity at different stations across the creek. So typically we want to have about 15 stations or 15 measurements across the width of the stream. If you have a really large water body, you may do more. If you have a very small water body, it may be hard to get 15 in. Our aim is to have each of the stations represent an approximately equal amount of flow. So if you have a deeper, more steady moving section of the creek, you want to do more stations in there than in the shallower, slower moving side parts of the creek. So at each of these stations, in this diagram you can see it's set up for a deeper water body where there are 2 measurements for these deeper portions and only 1 measurement for the shallower ones. In most of the water bodies that we'll be in, we'll only do 1 measurement at each station because it will be shallower. So at each station you measure where you are on this tape, so the location of your station. So we'll write down our distance along the tape, and here it's marked as D, or the D is actually for depth. So you'll mark your distance along the tape. We'll measure that for each station. We'll measure the depth of the water at that location, and I'll show you how to do that on the rod that the pygmy's attached to. So you'll mark down where you are, the depth of the water, and then you'll take your velocity measurement. For all of these velocity measurements, we require a measurement time of at least 40 seconds. So for the pygmy, what we'll do is we'll have somebody on the bank with a stopwatch who's timing 40 seconds, and they'll tell the person who's counting the revolutions of that pygmy meter how many times, when their time's up, and that person can then say how many times it's spun in 40 seconds. Especially if the pygmy meter is moving slowly, you may have to go beyond 40 seconds to get a full revolution. And so the person with the stopwatch shouldn't stop it until the person counting says to stop. So when we're done with one station, what we should have is the distance along the tape, the depth of water, and the number of revolutions and the amount of time that those revolutions took. So we should write down those 4 measurements for each station along our measurement. We will talk later in class about how to calculate a flow rate from that data. So in our field notes, I'm just going to reiterate this. You should have the distance from the bank. So this is our distance along the tape, our depth, and then our velocity will be made up of revolutions and time. And for the pygmy meter, there's a specific equation to relate revolutions per time into a water velocity. If you're using a different current meter, you may just get a velocity readout, and then you can use that. But essentially, we'll use the distance from the bank, our depth, and our velocity to calculate a cross-sectional area and our depth and our velocity, so that we can get our flow rate. Because we don't actually have the width of each of our sections, we really only have the distance along our tape. What we have to do is go back and create what's essentially an integral. So each of these stations is going to form the middle of a section of creek. So we're breaking the creek up into lots of little rectangles where the measurement's taken at the center of the rectangle. And so by using these distances along the tape, we're going to calculate a width of each of these rectangles. We measured the depth, and so we can use the width of the rectangle times the depth to get the area of each of these small rectangles, and we'll add all of them up to equal the cross-sectional area, or approximate the cross-sectional area of this whole section. So for smaller water bodies, or for shallower ones where the depth is less than 0.3 feet, so we can't use a current meter, we'll use a portable flume typically. So this is a picture of a portable flume. It folds up so that these wing walls fold back against the body of the flume. So the flume has different parts. This is what we call the throat. Throat is that narrow section in the middle, and those throats come in 1, 2, 4, and 8-inch widths. And so depending on the amount of water, we'll use different sizes. That variety in throat sizes allows this method to measure between 2.5 and 1,000 gallons per minute of flow. What we have to remember, though, is that when we set this up, all of the water has to go through the flume to be measured. So none of it can go under it or around it. So we have to pack in earth, ideally clay earth, underneath it, squidge it in and get it level, and then build up dams around these wing walls to keep the water from going around it or under those wing walls or under the body of the flume. So all has to go through the middle. We'll set one of these up in class, and you'll see that sometimes it can be easy and sometimes it can be challenging. So we have to pack it and level it to make sure that all the water is going through it, make sure it's level in both directions, and then what we're doing is we're recording the depth of water at the front of the flume before it goes through the throat. But our quality assurance, quality control on this, to make sure that we haven't just set it down in non-flowing water, and to make sure that there's enough velocity. The assumption here is that there's a free fall of water going out the back of the flume, and so we need the depth on the front of the flume to be 2 times that on the back of the flume. And so we record the depth on the front and the depth on the back to show our quality control measure. In some places, we can build what's called a weir in. And these are typically installations that are built in during construction so that you can easily go back and measure the flow rate very, very quickly and reliably. And so these are based So the most common type of these are called V-notch weirs, and it's a 90-degree V-shaped notch in the weir. And so this is looking straight on, this is looking to the side, so the weir would be installed to back water up behind it, and then the depth of water over top of that V is proportional to the flow rate going over that weir. So these are really, really great for quick, especially frequent measurements where you're going back to the same site over and over again to measure the flow rate. One of the limitations is that you can have sediment buildup behind here, and in a site that has a lot of sediment, you may have to clean out behind that weir very, very frequently. So I mentioned that we can do instantaneous measurements, so we just talked through the different methods for instantaneous measurements. There are also mechanisms for doing continuous measurement of flow. So the U.S. Geological Survey sets up these USGS gauge stations. We will look at some of the data from the USGS gauge station in Athens during class. So these measure the depth of water on a constant basis. And so we'll look at these online, but usually you can get data every 5 minutes for the depth of water. And then they go back and create what's called a stage-discharge relationship. And this is a mathematical relationship between the depth of water, or stage, and the discharge at that site. And so, the gauges record instantaneous stage, and then discharge is calculated from that stage. So the way that they do that is throughout a year they'll take at least 3 measurements at each site at different flow regimes, so at different depths of water. So at different depths of water, they'll measure the discharge at that site. So it used to be that they'd use those bridge cranes, the AAs set up on a bridge crane. Now they have a higher tech method that's quicker, but they'll have these different measurements of discharge at different stages, and they'll make a mathematical regression to correlate the stage to the discharge. This relationship is amended every year in case there are hydrologic changes at the site. So most of these gauge stations look essentially like this, where there's a connection between this gauge house and the creek. And so it'll usually be a piped connection. This is called a stilling well. And a stilling well basically is just a vertical pipe that allows the water in that pipe to be at the same level as it is in the creek. So when the creek is this height, the water should be this height. When the creek is at this height, the water should be at this height. And then there's a float or a transducer in that stilling well that records the depth, or that measures the depth, and it can be recorded and transmitted to the internet on a semi-instantaneous basis. So just showing, the sort of data that comes from one of these gauge stations. This is the gauge station in Clear Creek that's near Rockbridge, Ohio. And essentially what this is showing is the yellow line is the mean from 1939 to 2006. So this is a lot of years of data. And you can see that there's a typical pattern. So this is from January till the end of September. So you can see that there's a general pattern of a wetter spring and a drier summer. But then by plotting specific years, we can see the wet years versus the dry years, and how that distinction ends up being a little bit challenging. So 1988 was considered a very dry year, but we can see that in the summer there's basically almost no rain. We've got a couple of storms in the summer, but in that spring we had some high intensity storms still. And so while it was a dry summer, we still had a pretty wet spring, and so we may be able to, you can tease out more information from that. The pink one is from water year in 2006, and that was a wetter year, but what you can see is that while we had more storms throughout the year, we had many more summer storms, but the highest intensity storms in our wet year were lower than the highest intensity storm in the dry year. And so it lets us just have a little bit more information and assess that information a little bit better by having these long-term continuous records. So today we've talked about why we measure flow and different methods to measure flow rate or discharge. In our next video, we'll talk about applications of flow and how we can estimate flow when we're not able to measure it. Thank you for listening.